Again, I will keep it a little bit brief. We have a long session this one, and already Professor Das has already told us that we put the filter, but again, there is a design for the filter, which like most of the people like in our professions, we have a filter material, just go and put it there and it will automatically do. But people who are doing that, and this is mostly coming from the dams and levees. So in USA, the NRCS, that department, they saw that a lot of these filters are not working. So they come up with a proper design. So that's what I will little bit discuss here briefly. But we will again go details on this through a Excel spreadsheet during the tutor. So main two aspects of the filter. One is we are not allowing any fines particle to go through. So that's the first thing. Retaining of the fines particle, because these fines particles are causing all the effect and all the havoc is caused by these fine particles. If you retain that, then you are good. And second thing is, again, you allow the water to go, because that's like a drainage. Filter is like a drainage. So two things we have to check that. So this is one of the example, like we can put the filter and that can be used. So if you look at this, you have filter material and again there is your fines material. So you are designing the filter to retain the fines. So fines, you are not allowing fines to go there. So there should be a compatibility. So that compatibility we are looking at. So basically we have a base soil. That's what we saw, that we have a base soil, and for that base soil we are designing the filter. So that base soil, we have 4 different categories of base soil. So it can be fine seamed soil. Mostly we are looking into number 200 in in the US context we have the seed size numbers, but for the Indian context it's 0.075 millimeter. So anything above that, like if those material which go through the number 200 soil, what is the percent? So category 1 is higher than 85%, that means it's mostly fines. Then 40 to 85, then 15 to 39, then less than 15. So that's how we first categorize the base soil. And then there are filter criteria. We come up with the filtering criteria. So what should be the filter gradation? So depending on the base soil, this is the filtering criteria, and then there is other design criteria, like the filter has to be gap graded, or the filter band should have a limit, because when we design a filter we have a band, like we cannot say that exactly this will be the gradation. We give a range of gradation. That's why we have a lower level and upper level. And this gap graded also, we say that we will discuss more details. It's called coefficient of uniformity, D60 divided by D10. What should be the ratio? And it should not be higher than that. Then also we look into the segregation criteria. So these are all criteria, like we say that there should not be any, in the filter there should not be anything above than 3 inches. You see, that's the limit. Like that's why D100 should not be more than 3 inches. Yeah. So this is the step we will further discuss in the, we have Excel spreadsheet. So first we calculate what's our base soil, and if base soil material is larger than 4, then we do some correction, number 4. And if it is not higher than number 4 is 4.75 millimeter. If there is no more in the base soil more than, then we don't do the correction. So if it is more than that, we again correct it, correct the gradation. Then we first see the filtration requirement. What that filtration requirement is, the big D here is the filter, small d here is the base soil. That's how we are differentiating. So the D15 is the, what should be the maximum allowable D15, because that D15 controls the, because we are using it for the retention, no, like we are saying the fine should not pass through it. So to check that, we come up with the D15, and that D15 is related to D85 of the base soil. If D85 of the base soil is this, then D15 of the filter will be this. So that's where we see that maximum cannot pass through. Okay, maximum cannot pass through. Then the second part is the drainage, like the permeability requirement. Again, the permeability requirement allows what should be the minimum D15, because it has to drain through. It should allow the soil, not that it will block the flow through the soil. So maximum D15 for retaining and minimum D15 for the like make it drainage. So those are the two things we have to see. And then we have to make sure that coefficient of permeability should be less than 6. And also we have to see the ratio of maximum and minimum, like when we are saying the range, that should be the less than 5. Then we also come up with what should be our D5 and what should be our D100, and also we have some control of the what should be our D90, what should be our D10. So based on that we can go to the last one. So this is our base soil, and the base soil will be again regraded if it has any particle more than number 4, and based on that regraded we will come up with this design criteria. So you can see that number 1 point is coming from the step 5, number 2 point is coming from the step 7, number 3 is coming from the step 8, number 4 also coming from the step 8, and number 5 is coming from the step 9, and also number 6 coming from the step 9, and number 7 is coming from the step 10. So that's why we created the band, and it's just simply join it, and we have to make sure our filter gradation stays with this band. So then that filter can be effective filter. So this is kind of a filter design. We will discuss more, and I have a spreadsheet I can give it to you guys. You can also read it. Okay, I think that's all for this session.
Stop here.
Any question?
Do you have any questions?
I have a question. My questions to Dr. Das sir. So my questions are for you. Sir, in your slides, one term you have used zero airward line. Zero airward line. So practically it is not possible to achieve the zero airward. It is only theoretical, sir. So like how much maximum we can reduce the voids when we do the compaction? Up to how much percentage can we practically it is possible?
That depends upon the
Material. Okay. And for the zero air void line, 100% saturation in the soil is compulsory.
That is zero air water.
Compulsory.
That is either zero air water or 100%.
Zero air
That's
void
it.
means 100% saturation.
But sir, zero air void means all the voids are totally removed, so there is no void, sir.
That means filled with
Zero
water.
air void.
Filled with water.
That is saturated.
It is
Okay.
not zero void. This is zero air voids.
Zero air water.
So no air is there, but void in terms of water is still there.
Yes.
That will also expel when the loading will come from that. So
Yes.
that water will come
Yes,
out.
that is a consolidation. I would call it.
Consolidation, yes. Okay, so this is clear. One more question, sir. You mentioned about the lab permeability also. So I want to know that lab permeability results are how much valid or how much useful when we do the field permeability, or how reliable can it be interpreted in the actual field permeability case, sir?
I said that is a problem. That is a gap. What I said you. In the field for lab permeability, we are talking about through gravity how much this water is going on. And again also at what density I am compacting and giving the permeability. What moisture content I am giving the permeability. If it is getting simulated at the site, but still people have, I have got the data also, like what is the difference between the field permeability and lab permeability. Even if you consider all these things, still there may be 20-30% variation.
So field permeability is more reliable rather than doing conducting in the labs.
True,
Correct.
but it is not that easy to do in a field permeability.
Yeah, but some of the geotechnical agencies have the equipments which they perform at the field. So.
Yes, that is, that's you see what you are going for, when you are designing, your desirable permeability, how much it should be. Now, how you know that? You, after constructing, then they are going and checking that in situ. Okay?
Yeah.
But how I'll go for to achieve my design permeability? How to get that values? That is required through laboratory only.
Okay. But sir, before that, before constructing any structure, we do the field investigation. At that time itself, we get the
that is
field
field
permeability.
investigation of the natural soil.
Yeah.
But now
After
I am
construction.
constructing that is my tellings.
Okay. So that will vary. Then permeability will change totally. That is what you are saying.
Totally.
Okay.
And also field, what you are talking about, that not easy. Suppose say pumping in, pumping out, which is a common in groundwater,
Yeah.
that is not so easy to do it like in a laboratory. Cost effective and how many points you can do it. And any other empirical, in terms of electrical rigidity, electrical, all other things, is a correlation. It is a correlation. We have got also this, I'm correcting the name, we have got that equipments in the field permeability, what they are called. There is some other techniques are also there. But what they have been found, there is a variation, even if control everything and at the site where it goes, there is a variation.
So for designing, at the initial stage of the designing, field permeability data can be used in the design stage. After that, cannot be.
For groundwater penetration, you can use it. But for your tailing, you cannot. What's the use of it?
No, for other structures like plant structure or any other structure, building structure.
There you can use it.
That can be
use
used.
that.
That can be used.
That can.
Okay, sir. And sir, you said that one more point you discussed that when there is no water in the clay, you said that the Terzaghi's theory is not applicable for consolidation.
No. I said when it is unsaturated.
Yeah.
So suppose the Terzaghi assume that the soil is saturated.
So
Full, that is zero air void.
okay.
Only water.
Yeah.
But that is not the case in our most of the cases.
Yeah, in field. We will not achieve that. We will not achieve.
So that's why I said there is another concept we are talking about called unsaturated soil. I mean the consolidation. That is unsaturated. Soil is not saturated. Then which one? To the air which in between. So the how to take it out. So that way the theory becomes different.
Because in clays generally we calculate the settlement by that trapezoid 2:1 method, and we do the calculation of how much settlement is coming. That bearing pressure we consider for the foundation design.
So there
So
we
that's
assume
why.
that my clay is saturated.
That we have to assume.
It is assumed.
It
The
is
formula
already
is
assumed in that formula which we are calculating. It has been assumed.
Assumed.
Okay.
Which is not in your case most of the time.
Practical. Correct. That's it.
Okay, thank you. Anybody else?
I have sir, one observation that you have shown the flexible permeability apparatus
Uh-huh.
with the confining pressure and all, and you have shown that with the confining pressure the permeability value is going to decrease. So if I use or adopt the conventional flexibility or
Colligate,
apparatus, and will be on the conservative side for the design purpose.
Yes.
So
Because the permeability low.
will be on the safer side. If
No.
I consider
No.
we will get the higher permeability. So maybe
If you are going for impermeable case,
Uh-huh.
if you want to make it is like an impermeable one.
Okay.
Suppose if I want to check its permeability part, because now we are going for filter design. So in that case, phreatic line will get changed.
Yes.
The phreatic line will totally change because we had assumed something which is higher.
Yes.
Now it has come down.
Uh,
So the phreatic line will change. My filter, where I will place it? This filter design will based on the position of the phreatic line.
Yes.
That change will happen.
And sir, for you sir, you have shown that gradation part and filter design. You mentioned base soil. So for base soil, you mean telling materials?
Telling matter. Because you are putting the filter close to that. And one aspect is I said that it has to retain.
It's fully dry.
We should not allow this soil to go into there. Because if the base soil go into the filter, then filter will not work. That is what most of the time in the practice that occurs. I have seen
Water is
that.
present in the.
There is filter, there is everything, but still water is.
Thank you, sir.
Yeah, one thing I can mention when we are discussing, like how in the beginnings, when we first start the design, like his question, when we start the design, we do not have anything. There is no field data, nothing. But that's where we go into the literature and look into the things, but we have the tailings where we can do some laboratory tests. So initial design phase, laboratory testing is very important. Because like the permeability, you saw that wall permeameter where we can get the permeability at different stress condition. Because with the depth our stress condition is variable. So that will show us like the permeability can be lower and lower as you go deeper. So that those kind of concept we can apply that. But again, that is our first design concept. But as we go on and in the field we collect the data, then we will compare. Like this is our design, this is what we are seeing in the field. It can be different, then we modify and go. So that is the procedure should be followed in the tailings design. It's not that just one design you get that and go on doing it.
Correct.
Then when it fell, like then we come up and oh it fell, what will we do now? Not that. So that's why it's every stage. And you won't imagine how much money is being spent right now putting this operation of the design of the tailings dam. For each site, like just for design purposes, like we all do only the design, close to $3 to $5 million per year, like I'm telling per annum. Yeah.
Sir, what is the value of C and Phi for this red mud, ash and normal soil?
You are asking like what
yes,
what
sir.
should be the again?
I'll answer.
Depends on soil.
So when we are talking about red mud, in a very typical case, so the phi value is very high. Which says that the phi value can go up to 35 to 40 degree. And cohesion is less 25-30 degree, which is contrary to the soil. because red mud contains only 10 to 15% coarse grain material. Rest are silt and clay. But phi value is high. So for that, or the strength it shows high. So that's why now the studies, it could be due to sodium hydroxide presence there. So for that reason, now people are trying why it is showing so high value. Because by default we know in geotechnical civil engineering, coarse grain material high sodium.
Exactly.
But in the red mud, that's why I say it is very contrasting. It is only 10% coarse grain, 90% fine grain, but the phi value is very high. It went up to, in our case, it went up to 40 degree. I didn't share you the, then morning, sometimes I can share you the values. It went very high.
Because of?
Because of now the problem is there is one thing. One is the grain size or irregularity. Another part people are trying to explain it is like the presence of the sodium hydroxide trying to develop that friction, and which will be lost if this sodium hydroxide is leached out. I mean that what is there presently. So that way it is what the value it shows, that value should not be considered for the design. I mean if it is a long term when I am considering. That is the aspect of this red mud which is very difficult. For that reason also now people are trying to correlate with the CPT. Because what I was saying, CPT is a more realistic. Because when I am taking the sample from there and doing it in the laboratory, there are lots of aspects which makes it disturbed. We don't get the real picture of that material once I bring it here. But that conducting the CPT and interpreting the results is very tricky. I mean, those who have got the experience only have got that, even they don't know when to, how long to penetrate. So that I will get all the information. At what rate I should penetrate if I am getting this type of things. So that aspect is there, barring that. So obviously CPT, because it has been, that's why CPT has been modified to different. Initially when 30 years before we were doing it manually, only I was getting value, C5 value. But now you can get zero velocity, you can get pore water pressure. I mean, all these aspects is possible through CPT because it has been modernized like anything. Within 30-35 years. And now it is a truck mounted, anywhere you go and everything comes computerized, and it also gives the layering.
Correct.
And the SPT, we do it, conduct it as 45 centimeter. If you have got a layer of even 10 centimeter, it cannot detect. But whereas CPT can go up to 2 centimeter. I mean 20 millimeter gap also it can detect. So that is the aspect of the CPT. That's why people are going for. SPT is very good, and particularly in our trailings and other, the layers are different. For 45 centimeters is a big distance. We can have different layers.
So this C5 are constant here, this varies with the site situation. Like
It varies because
saturated drain, non-saturated drain.
yes, because that is
How
what.
it varies? How-
Yes, that is because when you are CPT is when I am talking about. In CPT also, what condition you are going for? Suppose if I do it quickly, it becomes a drain condition. Slowly I put it and allow to drain, it becomes a drain condition. So actually, in demonstration, I have called that guy. If he comes with the flexible trial, explain. Otherwise, with the existing, we can explain it. This what is this drain condition or drain condition? Because by default, people don't consider all these things when doing for the testing. There is a big, in fact, I have also observed this. So is there also, because now these aspects also been changed. It is not only that people are going for critical states of mechanics. What they C5, it is a very, what they are saying is a number. That number change with different condition. Suppose example, if I take on drain condition, it is only C. If I take drain condition, only 5.
So what is the critical condition we have to consider during stability analysis of
Yes.
pumping and dike design?
That is not a straightforward answer. You have to see design with a different condition.
Trial and error.
Not trial and error, it is scientific. So I have to use, if this is the condition, what will be the factor of safety? If this is the condition, what is the factor of safety? What could be the worst factor of safety if I want to become safe, better safe than sorry So I will go with the maximum factor, minimum factor of safety, and accordingly design it. Because all depends upon that, because this water pressure by the drainage, why it is important. This pore water pressure plays a big role in almost most of the tailing pots. Because effective stress is equal to total stress minus pore water pressure. If the pore water pressure increases, effective stress decreases, and there it falls. So what is C, phi, all these things go. So this is very important.
So sir, for drain condition, you said we have to consider phi 0.
Drain condition C0, only phi.
Only phi. So C will not be there at all in drain.
On drain condition opposite.
Question is soil.
So you have to, so it is not that who is testing. You have to tell him, my soil is like this, you should do it drain test or on drain test. Otherwise you will give some value. Even clay लेके drain test कर देगा, आपको दे देगा 5 or 20 degree, and question कुछ नहीं. So all depends upon that. That's why even for testing, you ask the doctors what he should test, what test to be done. Otherwise, laboratory will do the testing, but he does not want to test. So as an engineer, you have to tell him which type of test he should do it, which is appropriate for your project. So that's why the new concept, tailing dam design is a totally like what Dr. Ponda was just talking about. After 29, the concept has been changed. Because with everything that Brahma, just 2-3 months before, a big committee from different countries has visited, say that everything is safe. After 2 months it collapsed. Just imagine. Then all the know-how present those days failed. They were all big shots. It's not that they have got plenty of experience in tailing dams. The government was making every 2 or 3 years, they were visiting and then giving certificate, they were maintaining. And they gave a certificate, after 3 or 4 months it failed.
So the drain and on-drain condition, it depends upon the soil type, site condition. If we provide these liners, it will not allow any water to drain.
Not liners, rather drainage. Suppose you are allowing a drainage condition or you are not allowing a drainage condition. Another called short term or long term. If it is short term, drain also taking water, drain out also will take time. So that becomes on drain condition. But if you want to a long term strength, that means you have allowing sufficient time and doing it. That means drainage is sufficient term, so drainage condition will come. So this is called actually, that is one professor called this engineering, particularly this type of geotechnical engineering science, but its application is an art. I mean, those who know how to apply it, they become successful. I mean, things are there, but you don't know of art of applying. That's why, because suppose he knows 30 years, don't need anything. I mean, suppose he knows how to apply, where to apply what. So that with the experience, those who know the art of applying, they are famous. So, but basic knowledge is same for everybody. So you have to put your knowledge. This is the condition. I should go for a drain condition or drain condition. They are going for a temporary structure and a permanent structure. Can they provide a proper drainage or they cannot provide a proper drainage? So all these things considering, we find out the parameter of conducting appropriate tests.
But like if you see, I mentioned most of the design before 1980 or even before 2000, they were considering or assuming drain condition, because that's the concept was coming. When we put that, like first 50 feet of the first layer, for the second, when you are done going for the second layer, we assume that it is settled, water gone, is now a drained material. Because these are all, they are thinking these are all fine sands, mostly. These are tailings but fine sands, and this what the concept. That's how they are going and putting the second layer on top of that tailing. Because if you see the upstream dam, we are putting second layer on top of the tailings.
Without any liner.
Huh?
Without any liner.
No, like even if you put a layer also, what layer will do? Load will be still taken by the tailings below the layer. So that, somebody explained me that we put a layer. That layer has no role. Again, the load will be taken by the, say, if you have a strong layer and a weak layer, and you are loading it, which layer will take the load? Weak layer will take all the load. That the load will be concentrated more on the weak layer. So the people, if they think that we have put weak layer, strong layer, weak layer, strong layer, it will be stable. No. If weak layer fails, there is no role of strong layer. Coming to that P, like one of the example I can tell you, I was looking at a earth dam. There I saw these people have used P 43 degree. That's like in my lifetime, I never gone that high.
Very high.
Very high. Then I come up, like wanted to see why they have used 43. Because that particular earth dam consists of all kind of material, like boulders, gravel, cobble, and also fines. So all kind of material, and they got this number from the geophysics, from the seismic velocity. It was high because of the boulder. But geophysically it is a boulder. But when we come to look into the stability, the boulder doesn't play any role. The cobble, gravel doesn't play any role. Role is played by the finer soil. Because if finer soil will fail, boulder will go with it. So that's why the characterization is very important. We have to look for it, and even in the drilling, like when we do only drilling, even don't do CPT, we do drilling, look into the soil and see if the finer soil is present, and if in the soil there is water present, then those are the critical zones, weak zones. I call it like a weak zones, and that will govern everything. And in further discussion, I will show you some examples how we have treated those weak zones. And that controls CP, whatever material we say,
These are all
coming from the weak zones, that's the most important. Other thing doesn't matter.
I think their concern may be for the slope stability.
Yes.
So we are using C5.
Yeah.
So for conservative point of view, because generally when we are determining C5, considering the peak stress, because we are getting from the most stressor curve. So if you know the stress strain curve, clear? So there are 2 points, one is the peak stress, another is the residual stress. So if you get the C5 corresponding to residual stress, that will give you no value. And you can do the design for that condition, you will be on the safer side. Because that will give at a high strength.
Generally, theoretical reports don't give that stress strain curve.
Yes.
They give directly the
C5 value.
C5 value at the peak.
Values which are used in formula. Stability analysis.
Yeah, then again, like you have to go and see like what sample being tested. Is that sample represent my whole structure?
Field situation.
Exactly, field situation, you have to look at it.
Simulate that thing
Exactly.
in the laboratory, then it is reliable.
Exactly. So, is the fine soil, like I mentioned that we have to mainly focus on the fine soil. That's also kind of a conservative, but that's also very important. Because if you protect, if I say that even there will be no failure of my fine soil, then my structure is stable.